Alright, in this video we're going to just look at a random mixture of questions on various kinetics topics that should serve as a reasonably good review of some of the more conceptual things in this unit. This first question shows us a graph and says the reaction of two NOs and Cl2 producing two NOCls was performed and the following data obtained with constant concentration of chlorine. Now, you can pause the video if you want and try the question and then listen to my explanation afterwards if you like. So the first thing I notice in this graph is that it's a graph of the reciprocal of concentration versus time, which I remember is the test for a second-order process, and it's linear. So that tells me that the reaction is second order in NO. So it's got to be second order in NO. Is the following mechanism consistent with this data? Well, the slow step in this mechanism is step 2, that's the rate determining step, and so its rate law would be first order in NO and first order in NOCl2. So my first response would be, no, this doesn't look to be consistent because it's supposed to be second order in NO. Now, if the first step, and I'm wondering if there's actually a small mistake in this question, was supposed to be not only a fast step, but a fast reversible or a fast equilibrium step, then we remember that you could, for the first step, write the equilibrium expression, Kc would equal the concentration of the product, which in this case looks to be an intermediate, so NOCl2, over the concentration of the reactants, and everything here is raised to the power of their coefficients. So over NO concentration times Cl2 concentration. So that's called the equilibrium expression for the reaction. It's the ratio of product concentrations on top multiplied by each other, and each concentration raised to the power of its coefficient in the balanced equation. And in the denominator, the product of the reactant concentrations, again, each one raised to the power of its coefficient. Now, if you rearrange this, you'd see that the NOCl concentration is equal to Kc multiplied by these things in the denominator. If you then substituted that into the rate law for step 2, you would find that the rate law, which was equal to K, the rate constant, times NOCl2 concentration times NO, so at first it looks like it's just first order in NO. If you substitute Kc times the denominator of the equilibrium expression for NOCl2, you'd get K times Kc, which we could just call a new equilibrium constant, times NO and another NO, so times NO squared, and then Cl2. So it looks like if that first step was supposed to actually be a fast equilibrium step, then it would be consistent with what we see here, because the graph shows second order NO, and that shows second order NO as well. Does the linear plot guarantee that the overall order is second order? Well, since the linear plot only plots the NO concentration versus time, or in this case reciprocal of NO versus time, the Cl2 concentration is not actually shown here. So therefore we can't say anything about the Cl2's order looking at the plot. So therefore the plot does not guarantee an overall order of 2. In fact, in the example that we see here, the overall order would have been 3. It would have been second order in NO and first order in Cl2 if that was the actual mechanism. Alright, the second question, again, pause the video if you want to try it yourself, asks to classify each of these three reactions as unimolecular, bimolecular, or termolecular, and these refers to as the molecularity of the reaction. And so what we remember is a unimolecular process is a reaction where there's one particle decomposing. A bimolecular process has two particles colliding in a single step, And a termolecular process has 3 particles colliding in a single step. So the first reaction shows 3 particles colliding, so it would be a termolecular process. The second example has only 1 particle decomposing, that would be a unimolecular process. And the third one has 2 particles colliding, that would be a bimolecular process. Now note that in a termolecular process, the overall order had to be 3. In this example, we'd have, I guess this and this look like they're the same substance. They're an orange and a green atom stuck together. So there'd be 2 of those and then 1 of this double blue guy in the middle. So the rate law for that would have been rate equals K times the orange-green to the power of 2 and the blue-blue to the power of 1. So 2 plus 1, the overall order was a 3. In a unimolecular process, the overall order will be a 1, and in the bimolecular process, the overall order of that step would be a 2. Alright, so if you feel like it, pause the video and try this question. So we've got a graph that shows the concentration of a reactant over time for 2 different reactions, A and B. One of them is first order, one is second order. Which is the first order process, which is the second order process? How would we change each plot to make it linear? Well, in a graph of concentration versus time, the fact that they're not linear graphs right now tells us that they aren't zero order reactions, so we would say they're likely going to be first or second order. If you look closely, you can actually tell what the half-lives are and whether the half-lives are constant. So if we started with 1 molar concentration, let's look at curve A. The time needed to go from 1 to 0.5 looks to be about 50, 60, almost 70 minutes. Now the time to go from 0.5 in another half-life to 0.25, it's going to be a little hard to tell on this graph, but if we extrapolate, it's looking like it's not quite going to make it. So it looks like the second half-life might be longer than the first half-life, which leads me to think that that graph A is the second order process. In graph B, to go from 1 to 0.5 molarity took just under 50 seconds. To go from 0.5 molarity to 0.25 molarity took just under 100 seconds. So in graph B, it looks like the half-lives are actually the same, just under 50 seconds each. Therefore, graph B looks to be the first order process, and by default, graph A would be the second order process. To make them linear, if we were to graph the natural log of concentration versus time, then the first order process, graph B, would have become linear, a falling straight line. If we graphed reciprocal of concentration versus time, the graph A would have become linear, a rising straight line. So by inspection, we've got a reaction profile. We call these a potential energy diagram for reaction A becoming D. So how many intermediates are in this reaction? Well, the intermediates are the products of one step which become reactants in another step. So here we have the original reactants, here we have the final products. In step 1, which is here, this first hill, B would be the products of step 1, but they're also the reactants in step 2. So B is an intermediate, and C is another intermediate, because C is the product of step 2, but it becomes the reactants in step 3. So how many intermediates there are? It looks to be that there's 2 intermediates. How many transition states are there? Well, the transition state is also known as the activated complex, and it's what forms at the very moment of collision between reactant particles. Their potential energy goes to a maximum at that point. It's very short-lived, and it's neither reactants nor yet products. So the transition state would occur here in the first step, here in the second step, and here in the third step. There's 3 transition states, 3 activated complexes. Which is the fastest step? Well, the fastest step would have the lowest activation energy. In the first step, the activation energy would be this difference here, Okay? In the second step, it's this difference here, and in the third step, it's this difference here. So the one that's smallest, it's actually a little hard to tell with the naked eye, but the fastest step, I'd actually probably want to grab a ruler to be sure, but I'm going to guess that it's probably step 3. It's really hard to tell. What they probably should have asked instead would be which was the slowest step. That would be much more obvious. Step 1 is the slowest step because it clearly has the largest activation energy. Which step has the smallest rate constant? Well, the smallest rate constant is another way of saying if all the concentrations are the same, which step is slowest, the step with the slowest or smallest rate constant. That would be step 1, which had the largest EA. Is the first step of the mechanism exothermic or endothermic? Well, in step 1, we began with this potential energy here, and we finished step 1 with the potential energy higher than it began, so therefore it must have absorbed energy. Step 1 was endothermic. The overall process from A to D looks to be slightly exothermic, since the final products end up having less energy than we began with. All right, here's a conceptual question that deserves a little bit of attention, so pause the video and try this yourself, definitely. So we've got the relative rates of this reaction between atoms of A and molecules of C in vessels 1 to 4, and it tells us the relative rates are 1 to 1 to 2 to 3. What does that mean? Well, it means that the rate of reaction in situation 1 and 2 are the same, that's 1 to 1, but the rate in vessel 3 is twice as high as the rates in vessels 1 to 2, and the rate in vessel 4 is 3 times as high as the rates in 1 and 2. The red atoms, or the red spheres are I would say atoms, blue spheres are B atoms, and C2 molecules are in yellow. So what's the order of the reaction in A, B, and C2? Well, if we compare vessels 1 and 2, we notice that the C2, the yellows, are the same, there's 2 in each. The blues, the Bs, are the same, there's 2 in each, while the reds have doubled. So to go from vessel 1 to vessel 2, we've doubled the A concentration while holding everything else constant. Because of that, we notice the rate did not change. It stayed as a 1 to 1 ratio, so therefore the A must be 0 order, since it did not affect the rate. Now what about vessel 3? Vessel 3 compared to vessel 2, or compared to vessel 1, actually let's compare to vessel 1, has the same amount of A, the reds are the same in 1 and 3, the same amount of Bs, the blues are the same in 1 and 3, but it has twice as much C2. We've got 4 C2s versus only 2 in vessel 1. And we know that so we've doubled the C2. That doubling of C2 caused the rate to double. Notice the rate was twice as high as it was in the first 2 containers. Since we doubled the C2 and that doubled the rate is proportional to C2, so C2 must be first order. Now what about this B? B did not appear in the overall reaction, so at first that's a little confusing, but let's take a look. If we compare vessel 1 to vessel 4, where the A's are the same, there's 2 and 2, the C2s are the same, there's 2 and 2, but in vessel 1 we had 2 B's, while in vessel 4 we have 6 B's. So we tripled the B's from vessel 1 to vessel 4, and if we look at the relative rates, rate 1, vessel 1 was a 1, the vessel 4 rate was a 3. So tripling the B's tripled the rate, which suggests that B is also first order. So if we write a rate law, we could say rate equals K times A to the 0, C2 to the 1, B to the 1. Now, since the A was 0 order, you actually don't need to include that. You could leave the A to the 0 out of your rate law and you'd be fine. Write a mechanism that would agree with the rate law. Well, this is a little hard. We haven't done this yet, writing a mechanism before. But notice that the rate law shows first order B and first order C2. So one thing that would suggest is that perhaps an atom of B collides with a molecule of C2. And this would be the slow step of our mechanism because those coefficients match the orders in the rate law. Now, since B did not show up in the overall reaction, we're going to have to assume here that B, since it's a reactant here, would have to be a catalyst. So at some point, the B has to be produced as well. We also need 2 atoms of A to come in here as well. So what we need to do is apply some creativity, but we also know that we need to end up with 2 A's reacting with a C2, and we need to get 2 ACs as our overall reaction. I'm going to propose a 2-step process for this, step 1 being the slow step so that its coefficients match our rate law. Step 2 then is going to be a faster step. Now, from this point, all I'm going to do is apply some creativity and some logic. So let me just grab a different color for my pen. So what we've done so far is step 1 matches the rate law, and therefore B and 1B and 1C2, because our rate law was first order in those 2 things, and then the overall reaction has to be produced. So whatever's going to be now in green is logic. So what could I produce if a B collides with a C2? Well, there's, I guess, more than one possible answer to that, but could we get AC as a product there? We need ACs as product. I don't see any way to get an AC out of that collision. So I'm going to suggest that what we simply do there is do a synthesis reaction. So we're going to get BC2. Now someone else might say, well, let's produce a BC and a C. That's possible, but I'm going to suggest this is a little simpler. Now this BC2 product is not in our overall reaction at the top. So therefore, if we've produced it in step 1, we have to get rid of it in step 2. So the BC2 is going to be an intermediate. Now, what are we missing? Well, the overall reaction has a C2. Well, we've already used a C2. It has no B's, and yet we've used a B, so I guess we have to produce a B in step 2 to cancel it out. There's our catalyst. And then we need 2 A's as reactants still, and we need 2 ACs as products. Well, let's throw these 2 A's in here. So I'm making step 2 a termolecular step, which is possible. 3 particles collide. Now, is it possible in this collision of the 3 particles that the B will come out? Sure, I can imagine that. That I'm left with 2 A's and 2 C's. Well, I need to produce 2 ACs. So I'm going to just suggest that that's my other product. So you can see how that works algebraically. Whether it works chemically or not is a totally different question, if these were real substances. But algebraically, that works. So there's a mechanism involving 2 steps that adds up to give our overall reaction. The BC2 is an intermediate, so it cancels out. The B's are catalysts, so they cancel out. And we're left with 2 A's, 1 C2, and 2 ACs. And in this mechanism, our slow step has coefficients that match the orders in our rate law. There we go. A little bit of an easier question. Give your brain a break. Which of the following describes the above system? Well, in the reverse reaction, we'd be starting at the right and reading the diagram backwards. And if we did that, the activation energy in the reverse reaction would be here, this difference. And so if we go from 130 to 140, the activation energy would have been 10. So both A and B are looking pretty good from an activation energy perspective. The delta H is the difference from your reactants to products, so that would be this difference here, which, if we're going in reverse, is a negative sign again, and it go from 130 to 110 would be negative 20. So A is looking pretty good. What about C and D? Well, in the forward direction, the activation energy, let me just grab a different color of ink, the activation energy would have been this difference here. And so from 110 to 140, the activation energy would have been 30. So that would rule out D. It can't be. And what about delta H? Well, delta H would have still been this arrow here, difference from reactants to products. So notice delta H is the same difference, whether you go forwards or backwards. But in the forward direction, we would be going up in energy. So that's an endothermic process. So instead of being from 110 to 130, it would be positive 20 instead of negative 20 that we had earlier. So since it's positive 20, that rules out choice D. So only in choice A did we have a correct activation energy and a correct heat of reaction, delta H. Another conceptual question, the molecular scenes below are first-order reactions in which cyclopropane, the red particles, are converted to propene, the green particles. Well, if we do some counting, we need a half-life and we need the rate constant. So if we do some counting, we had 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. We had 12 particles to begin with that were red. After 20 minutes, we have 1, 2, 3, 4, 5, 6, 7, 8 reds. And we have, use green color, we have 1, 2, 3, 4 greens. After 60 minutes total, we're now down to, well, actually greens. We have 1, 2, 3, 4, 5, 6, 7, 8, 9 greens, and we're left with only 3 reds at that point. So we need to know the half-life and the rate constant. Well, at first I thought this might be a relatively simple question. If we had gone from 12 reds to 6 reds, we could tell easily what the half-life was. Or even if we'd gone from 8 to 4, we could tell what the half-life was. Since we didn't have a nice drop in reds like that, I think we're going to have to use the integrated rate law. So the natural log of the A, we'll use the red particles, or the reactants that are disappearing. So the natural log of 8, which is the amount left after 20 minutes, would equal negative KT, the time was 20 minutes, plus the natural log of the original amount, which was 12 particles. So if we solve that for K, we get the natural log of 8 minus the natural log of 12 equals, and then divide that by negative 20, and I get the rate constant is 0.0203. The units for that would be minutes to the minus 1. First order processes have time to the minus 1 as their units for K. The half-life then is, for a first order process, 0.693 divided by K. So in this case, 0.693 divided by 0.0203, and I get 34.1, and to be consistent with the units, that would be 34.1 minutes. So there's the rate constant and the half-life. This next question, we need to fill in the blanks in this reaction mechanism. There's 3 steps. This looks like some kind of catalyzed reaction with platinum metal. And then we need an overall reaction of 2 NOs producing N2 and O2. So let's take a look here. Notice there is platinum as a reactant in step 1, so platinum has to be a product somewhere, and sure enough, it's a product in step 3. So platinum is definitely a catalyst here. It does not show up in the overall process. Step 2 begins with NOPT, so the NO bonds to the platinum, which means it has to be an intermediate because it's being used in step 2, and I can see step 1 easily producing that product. So the NO initially binds to the platinum metal, forming NOPT. Now in step 2, the NOPT collides with an NO particle, or more likely the NO particle comes in and collides with the NO bonded to the platinum. Now, one of the products, if we look at step 3, there's a reactant O2PT. So we have to get O2PT, which means that'll be another intermediate. Now, what else could be produced there? Well, if we just add it up, we've got 2 O's and a platinum. We've already used those. There's 2 nitrogen atoms left in step 2. And in our overall products, we do need a nitrogen molecule, so let's produce N2. And now, if we cancel out the NOPT, the O2PT, and the platinum, we have the overall reaction that we wanted. 2 NOs become N2 and O2. So the correct blanks, we've got them: NOPT, O2PT, and nitrogen gas. All right, this next question is probably going to need a little more attention as well. So concentration of A as a function of time for the reaction A becomes products was plotted. Use the data from the graph to find the order of the reaction, the rate constant K, the rate of the reaction when time is 3.5 minutes, using parts A and B, and the rate at 5 minutes using slope, and then the initial rate of the reaction. Okay. Pause the video and try that yourself. Okay, so we've seen this already, that the order of the reaction, if we think that we go from 1 molar to 0.5 molar in just over 2 minutes, and from 0.5 molar we go to 0.25 molar in just over 5 minutes, or sorry, just under 5 minutes, so that because the half-life is constant, we would say that the answer to part A is first order. Okay, a constant half-life means that the order was first order. What's the value of the rate constant? Well, if we estimate the half-life looks to be just more than 2 minutes, so I'm going to estimate that the half-life is about 2.3 minutes. So now I can say the rate constant is 0.693 over the half-life. I just did a bit of algebra there. And so 0.693 divided by 2.3, we get 0.30 minutes to the minus 1. Now that we've got the rate constant and we know it's first order, can we find the rate when the time is 3.5 minutes? Well, to do that, we'll use the differential rate law. The rate equals K times A to the power of 1. That was first order. Since A is, yes, can we do that? Yes, we will. What we'll need to do is look at the graph at 3.5 minutes, and we'll need to get the concentration of A at that time. So at 3.5 minutes, the concentration of A looks to be bigger than 0.3, but not yet 0.4. So I'm going to estimate about 0.35. So the rate will equal our rate constant, 0.3, times 0.35, the concentration of A at that time, to the power of 1. So 0.3 times 0.35, it's about 0.11, and that'll be molarity per minute. The other way to find rate is to use the slope of a tangent line on a graph of concentration versus time. So at 5 minutes, they've drawn us a tangent line, so we just need to find the slope of that tangent line. There's a point over here. That point's coordinates look to be 3, well, again, it's bigger than 0.3. It looks to be about 0.35, 0.36 again. It's just an estimate. And then I'll need another point. Maybe I'll use this point. How about the point right at 5? So that point there, 5, and then it looks to be just slightly more than 0.2, so 0.21. So now that I've got 2 points, just use your slope formula. 0.36 minus 0.21 equals, and 3 minus 5 is 2, so divide that by -2. I get a rate of negative 0.075, and we're probably going to get slightly different answers depending on your reading of coordinates, molarity per minute. It's negative because it's a negative slope. The reactant is disappearing over time, so the rate will be negative. What was the initial rate of the reaction? Well, the initial rate would be when the concentration was 1 molar. So if we just use the rate law, we'd get rate equals 0.3 times 1. So the rate was 0.3 at the very beginning of this reaction. 0.3 molarity per minute. All right, this is the final question in the video. The scenes below represent initial reaction mixtures, 4 of them, for the reaction of A and B, blue and yellow, with and without a solid catalyst, a solid present. The gray cubes are a solid. The initial rate, which is defined in the question as the change in A over change in time. Now, since A is a reactant, we know that that would give us a negative answer, so they're throwing a negative sign in front to make the rates positive. So the rates are going to be moles per liter per second. It's shown with each sphere representing 0.01 moles and the container volumes 0.5 liters. Okay, so we've got these rates shown. 4 rates. What's the rate law in the absence of a catalyst? Well, if we look at beaker 1 to beaker flask 1 to flask 2, in flask 1 the blues were the A particles. So in flask 1 the concentration of A, let's just make a little table here, A, B, and rate. So in trial 1 the rate was 3.5 times 10 to the minus 4. The A's in trial 1 went from 5 particles. So 5 times 0.01, it's 0.05, divided by 0.5, so it was 0.1 molarity. Each particle is 0.01 moles and the volume is 0.5 liters. The B's, which are the yellow particles, there were 5 of them, so that's going to be the same thing, 0.1 molarity. In beaker 2, 5.6 times 10 to the minus 4, we had the blue particles 5, 6, 7, 8, so 8 times 0.01, and then divide by 0.5. We get 0.16 molarity, and then the yellows stayed the same. So I'm not sure if I'm cheating here in terms of the spirit of the question. I'm translating the particles, the particulate representation, into a more familiar to me tabular with numbers kind of representation. In the third situation, the rate is still 5.6 times 10 to the minus 4. The blue particles, the A's, 5, 6, there's still 8 of them, so 0.16 molarity. And the yellow particles, 4, there's 8 of them, so 0.16 molarity. So now that I've got a table set up, we can just go ahead and find the rate law. So what I'll do is I'll use rate 2 divided by rate 1, that's 5.6 divided by 3.5 is 1.6. On paper on a free response question, you'd show all of your work. I'm just taking some shortcuts there. So I divided rate 2 by rate 1, and I get this. That's going to equal, the B concentrations would cancel. The A's, I'm going to get 0.16 to the power of x divided by 0.1 to the power of x, which is equal to 1.6 to the power of x. So therefore, x, which is the order for A, is a 1. If I do the same thing with trials 2 and 3, I'll divide their rates, 5.6 divided by 5.6, I get 1. The A's will just cancel, as will the rate constants. I don't think I said that earlier. And we'll be left with 0.6 to the y divided by 0.1 to the y, which is 1.6 to the power of y. Therefore, y, which is the order for B, has to be 0. So the rate law in the absence of the catalyst would be first order in A and zero order in B. What's the overall reaction order? Well, 1 plus 0 is 1. The rate constant, we can take any one of those three trials and plug them in. The rate constant K would be the rate divided by the concentration of A. So if I look at trial 1, for example, 3.5 times 10 to the minus 4 divided by 0.1 is going to be 3.5 times 10 to the minus 3. And that'll be units of, I guess that'll be units of just, what were the time units here? Seconds. So it was moles per liter per second in the rates. So the rate constant there would be 3.5 times 10 to the minus 3 per seconds. Okay, so I just took the rate in trial 1, I divided by the concentration of A in trial 1. You could do that theoretically for any of the trials and you should get the same answer. Do the gray cubes have a catalytic effect? Well, in the final container, we see that the concentration of the blue spheres, the A's, 1, 2, 3, 4, 5, in the trial 4, we have 0.1 molar A, and the yellows, we still have 1, 2, 3, 4, we have 8 of them, so we have 0.16 B's. And then the rate is 4.9 times 10 to the minus 4. So did those gray blocks act as a catalyst or not? Well, we know that the rate is equal to Ka, and the A there is 0.1 molar. So the rate in this fourth trial should have been the same as the rate in trial 1 if only the concentrations of A and B were considered. So in trial 1, the concentration of A was 0.1. In trial 4, it's still 0.1, so the A concentration did not change. Therefore, the rate should not have changed. But instead, we see the rate increased. So since the rate increased, while B didn't change, in fact, B is zero order, so B doesn't really affect anything, the only way to explain that increase in rate, if the temperatures are the same, would be if, yes, the gray blocks are acting as a catalyst. So they increased the rate of the reaction, therefore, yes, they're having a catalytic effect. So I hope that helps. About 35-40 minutes of review, some calculations, some conceptual things for kinetics. Be sure you practice finding differential rate laws using the method of initial rates. Be sure you can do it showing your work, finding rate constants using that information as well. Looking at the rate of given in a table and finding the rate of some other reactant or product in the balanced equation using stoichiometry. Be sure you're also comfortable with integrated rate law problems, as well graphically as well as word problems, and that you're also familiar with the Arrhenius equation as well.